Hello students, how are you? Today we are going to discuss numericals of 2nd PU Physics Chapter 2, Electric Potential and Capacitance. So we know that from first chapter or second chapter, one 5 marks theory question will be asked as well as one 5 marks numerical will be asked. So compared to first chapter, the numericals of second chapter is very important because in first chapter there are 5 marks theory questions. Okay, so that is derive an expression for electric field due to dipole on an axial line, derive an expression for electric field due to dipole on an equatorial line, and the application of Gauss law. There are 3 application of Gauss law. Total 5 derivation will be asked for 5 marks. So therefore, it is always important to read numericals of second chapter, that is electric potential and capacitance. And the numericals is usually based on work done in moving a charge from one point to another point on a square, okay, or the charges are placed on a rectangle and we need to find out work done in bringing a charge from infinity to the center, or some points will be given like this, and electric potential due to single charge or electric potential due to dipole, or we need to find out the null point, and we need to find out capacitance of the capacitors when 2 or 3 capacitors are connected in series or in parallel, and capacitors related numericals will be asked in this lesson. So that's why it is always important to read the numericals, or you practice the numericals of second lesson than first lesson. So today we are going to discuss numericals of this lesson, and here is a list of formulas. Now the first question is 3 capacitors of capacitance 3 microfarad, 6 microfarad and 9 microfarad are connected in series. Then find the capacitance of the combination. And the second one is, if this combination is connected to 60 volt supply, then what is the potential difference across 9 microfarad capacitor? So you have to find out effective capacitance, that is the first question. And the second one is, you need to calculate V3, okay, potential difference across the third capacitor, that is 9 microfarad capacitor. So for this, let us use this formula. 1 by Cs is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over Cs is equal to, substitute now, just write the number 1 by 3, 1 by 6 plus 1 by 9. So it is understood that here there is a microfarad. No need of writing, so let it be as it is. Now, what is the LCM of this? 3, 6 and 9. So let us take it as 18. By 11, and if you divide 18 by 11, it is found to be equal to 1.63 microfarad. 1.63 microfarad. So here the answer should be lesser than, least out of these 3. So least is 3, it should be less than that. So the answer is 18 by 11 or 1 by 1.63 microfarad is the answer. And we need to calculate V3. For that, see here, when 3 capacitors are connected in series, when the capacitors are in series, which is common here? Charge is common. Charge is common. And if the combination is replaced by single capacitor and whose capacitance is nothing but Cs, okay, and if you connect this to battery of voltage 60 volt, then what is the charge? Charge on the single is Cs into V. How to calculate? Cs into V. So let us write Cs as 18 by 11 into V is 6. So the answer is 98.18. And here there is a micros. So let us write it as micro coulomb. Then how to find out V3? So charges on each capacitor is same as charge on the combination. Okay, all the 3 as having same charge as that of its combination. Therefore, let us use this relation Q is equal to CV and we know C3, right? So, then how to calculate V3? V3 is equal to Q divided by C3. So, Q is how much? 98.18 microcoulomb, that is minus 6, 10 power minus 6, divided by C3 is 9 into 10 power minus 6. See, micro cancel. Now, let us divide this 98.18 divided by 9, which gives 10.9. 10.9 volt is the answer. Yes, students, please go through it properly. When capacitors are connected in series, this is a way of calculating effective capacitance. See, usually what happens if you forget to write left hand side term, then you will calculate this number, no? So, you will consider this as CS. So, that's why please write the left hand side term, that is 1 over CS you are calculating first and take reciprocal of the answer. Reciprocal of that number gives CS. And when they are connected in series, the charge remains same, which is as that of the combination, right? So, here charge on single is same as charge on each capacitor. That's why first let us calculate charge on the single capacitor using the formula CS into V. So, therefore, we'll come to know what is a charge on each capacitor. So, use this relation to find out potential difference across each of the capacitor. Okay. So, after adding these three, we need to get 60 volt. So, V is equal to V1 plus V2 plus V3. The next question is, in a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 power minus 3 meter square and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. See, initially in a parallel plate capacitor, there is just air in between the plates and area and the distance between the plate is given. So, we need to find out capacitance of the capacitor. And if the space between the plates is completely filled with dielectric medium of dielectric constant 6, what will be the new capacitance? So, for this we are using this relation capacitance of parallel plate capacitor. Students, don't be confused with the parallel combination. Okay, parallel combination means the capacitors will be mentioned, right? 2 or 3 capacitors are connected in parallel. That is different. Parallel plate capacitor is different. See, here we know that capacitor is having 2 plates, right? It may be cylindrical in shape or it may be parallel plates, rectangular plates or spherical plates, right? So, here there are parallel plates. Plates are parallel to each other, right? Rectangular plates are parallel to each other. So, that capacitor is called as parallel plate capacitor. And air is in between this, right? So, there is nothing in between. So, only air is between the plates. Then area and distance is given. So, let us use this formula. Epsilon naught is 8.85 in 10 power minus 12. So, that number you should remember. Sometimes it will be given, but most of the time you have to remember this number. 8.85 in 10 to the power minus 12. Substituting area and distance between the plates. See, here 10 power minus 3 get cancelled. 3 ones are 3 twos are. Multiply 8.85 by 2, you will get 17.7 picofarad. And when this place is filled by dielectric constant K is 6, then just write K here, okay? In a place of this epsilon naught, you just write K into epsilon naught and substituting will get this number as 106.2 picofarad. So, therefore, as dielectric is introduced in the plate between the parallel plate capacitor, then what happens? Capacitance get increases. One more question. An 800 picofarad capacitor is charged by 100 volt battery. How much energy is stored by the capacitor? The capacitor is disconnected from the battery and connected to another 800 picofarad capacitor. What is the electrostatic energy of the system? See, here initially one capacitor, that is 800 picofarad, is connected to 100 volt battery. Then what happens? This capacitor starts charging and its energy increases. Capacitor is used to store charges and hence it stores energy, electrostatic energy. Then how to find out energy? U is equal to half C1 V1 square. So, half CV square is a formula. Let us consider this is C1 and this is V1. Okay, so substituting will get 4 microfarad. Is it clear? So substitute C1 as 800 pico. Pico is 10 to the power minus 12 and 100 volt. 100 volt you need to square this 100 square and divided by 2 gives 4 microfarad. Now you replace this. Disconnect this battery. Replace this battery by another 800 picofarad capacitor which is uncharged. Okay. And what happens when you connect like this? This is already stored. Okay, I mean the charges are stored in this first capacitor. Now it acts like a battery. Okay, so once you connect this charged capacitor to uncharged capacitor, then immediately charges flows from higher potential to lower potential. Charges always flows from higher to lower, right? So here this first capacitor shares its charges with the second capacitor, and the potential will be common across these two. Okay, as the charges flows from higher potential to lower potential, after some time what happens, both will be at a same charge, same potential. Okay, both will be having equal potential. By that time charging stops. Okay, so the charge is not flowing further. Once both the capacitors are having same potential, then it is called as common potential, and we can use this formula to find out common potential. That is V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. These two capacitor, when they are connected in parallel, they are having common potential. So that common potential can be calculated using this relation. So here C1 800 picofarad, V1 is 100, whereas V2 means the second one is uncharged initially, right? So therefore there is no potential across the second capacitor. So therefore V2 is 0. V2 into C2 is 0. Second term reduces to 0 divided by C1 plus C2. Since they are connected in parallel, effective capacitance is C1 plus C2. Okay, substituting will get common potential as 50 volt. Now, what is the electrostatic energy stored in this combination? So, that is U dash is half Cp V square. Let us calculate U dash by using this formula, half Cp V square, and substituting will get this relation 2 microfarad. So, you are observing that when one is connected across a battery, the energy stored in one capacitor is 4 microfarad, whereas when this is connected across uncharged capacitor, then energy stored on this combination reduces to 2 microfarad. Then what is the loss in energy? It is 2 microfarad. Student, the next one is two capacitors of capacitances 2 microfarad and 8 microfarad are connected in series, and the resulting combination is connected to across 300 volt battery. Calculate charge, potential difference and the energy stored in each capacitor. So here there are two capacitors 2 microfarad and 8 microfarad which are connected in series across a battery of voltage 300 volt. Then what happens? These capacitors start charging as you switch on the battery. The charges on each capacitor is same and voltage is different. So when two or more than two capacitors are connected in series, charge remains the same. Then how to find out charge on each capacitor and voltage across each capacitor? First let us calculate CS. How to calculate CS? Since there are only two, so let us use this formula C1 C2 divided by C1 plus C2. How to get this formula? See, we know that 1 by CS is equal to 1 by C1 1 by C2. So we can write this as C1 C2 is LCR, cross multiplying, it is C1 plus C2, or CS can be written as C1 C2 by C1 plus C2. So let us use this formula. CS is product of two capacitor divided by sum of two capacitor. So multiply 2 into 8 into 10 to the power minus 12, minus 6 into minus 6 is minus 12 divided by 8 plus 2 is 10. 10 into 10 to the power minus 6. Minus 6 is common, right? 10 to the power minus 6. So therefore, it is 8 2s are 16 by 10 into 10 to the power minus 6. So what is the answer? CS is 8 by 5 microfarad. Now let us calculate Q. Charge on each is same as charge on the combination. So which is CS into V. It is 8 by 5. Micro is 10 to the power minus 6 into V is 300. 300. So 5 ones are 5, 6. And here 6 8s are 48. And 10 to the power minus 6, let us write 480. Say 8 6 are 48, 480 micro. So micro coulomb, 480 micro coulomb. Then what is the answer to first question? Charge on each capacitor is 480 microcoulomb. Now let us calculate this V1 and V2. We know this relation Q is equal to CV. So then how to calculate V1? V1 is a voltage or potential difference across the first one, which is Q divided by C1. So Q is 480 microcoulomb. 480 micro 10 to the power minus 6 divided by C1 is 2 micro, 2 into 10 to the power minus 6. This is cancelled. 480 by 2 is 240. Okay, V1 is 240 volt. V1 is 240 volt. Similarly, V2 is Q divided by C2. So Q is 480 micro 10 to the power minus 6 and C2 is 8. It is 60 volt. And after adding V1 and V2, you should get 300. So let us check this. 240 plus 60 is 300 volt. So then it is correct. Now next one is energy stored on each capacitor. Energy on each capacitor is U1 is half C1 V square. So half C1 is 2 micro 10 to the power minus 6 and V1 is 240. Multiply this 240 twice into 240. 2 cancel. So 240 square. So after calculating, we'll get 57.6 millijoule. And similarly, energy stored on second capacitor is half C2 V2 square. Substituting, we'll get 14.4 millijoule. Okay. Yes, students, solve this question and comment the answer in comment section. 3 capacitors, 3 microfarad, 4 microfarad and 6 microfarad are connected in series. Find the effective capacitance of the combination. Find the potential across 4 microfarad capacitor if the combination is connected to 100 volt supply.